Entropy is a measure of randomness or disorder of a system. And we can write entropy using the statistical mechanics definition as the Boltzmann constant multiplied by the natural log of the number of microstates that the system can occupy. So for example, if a solid, being ice, changes phase into a liquid, and if you take a snapshot of this system at the microscale at different times, you'll see that the molecules can occupy more positions and thereby can occupy more microstates. But at the macroscopic scale, you'll see that the water pretty much looks the same because you're taking the average behavior of a large system of these molecules. And when a liquid changes phase into a gas, the intermolecular forces become less significant, and therefore the particles can occupy more positions and more microstates than water. And we can thereby see that the entropy or disorder of the system increases from the solid phase to the liquid phase to the gas phase. Consider the following state for a gas, which initially occupies volume 1, so it has an entropy S1, and if we remove the stopcock, the gas occupies both volumes, so we'd have molecules entering volume 2, and these are all flying off at some random velocities. And we assume that this volume increase occurred at a constant temperature. So for example, you may be inputting heat into the system to keep the temperature constant. So when the gas occupies a larger volume, the particles will have more microstates, and therefore the entropy increases. So the entropy of state 1 is less than that of state 2. So therefore the entropy increases with an increase in volume. And suppose the gas occupies volume 1 and the temperature of the gas is increased, then the molecules are going to fly around faster, and therefore the disorder of the system is also going to increase. Suppose we have a reaction involving gas phase reactants or products. So in this case, ammonia and oxygen are in a gaseous state and react to produce nitrogen gas and water vapor. So we have the entropy of the reactants and the entropy of the products. And because we have less moles of the reactants, being 7, compared to 8 moles of product, then the product will occupy more microstates, and therefore the disorder or entropy of the products is higher than that of the reactants. Suppose we have the following distributions of gas particle velocities with an increasing temperature. And recall that the temperature is proportional to the average kinetic energy of the system, and the kinetic energy of a gas particle was 1/2 by the mass by the speed squared. So temperature 3 has a larger distribution of gas particle velocities and thereby has a broader distribution of kinetic energy of the gas particles with an increase in temperature. And consequently, as the temperature increases, the disorder or randomness or entropy of the system increases. The absolute entropy is measured relative to absolute zero, where you have a perfectly solid crystal and that has 1 microstate. So according to Boltzmann's equation, and that gives S equals 0. So at absolute zero, you don't see rotations of molecules or oscillations of the atoms relative to each other. And note that absolute zero has not been experimentally reached. And typically the absolute entropy is measured as the standard entropy, which is thereby always greater than 0, and calculated at 25 degrees Celsius or 298 Kelvin. And entropy typically has units of joules per Kelvin, so heat on temperature, but is presented as joules per mole Kelvin for different substances. So therefore a change in entropy between 2 states is the difference between the entropy in the final state minus that in the initial state. And in general, we'll look at chemical reactions where the change in entropy is equal to the sum of the absolute entropies of the products minus the entropies of the reactants. Calculate the standard entropy change for the following reaction. So the standard entropy change of the reaction is equal to the sum of the standard entropies of the products minus the sum of the standard entropies of the reactants. So for the products, we have 2 moles of ammonia, and we multiply that by the standard entropy of ammonia given in the table. And we do the same for the reactants. So we had 1 mole of nitrogen gas multiplied by the standard entropy, and 3 moles of hydrogen gas by the standard entropy of hydrogen gas, which gives the following result. And the units are joules per Kelvin. We have 2 moles of ammonia per mole of reaction. So that means the same thing. The Gibbs free energy is defined as the enthalpy minus the temperature in Kelvin multiplied by the entropy. And here we apply it to chemical reactions, where under a standard state we put zeros here, and the standard state refers to pure substances, or gases at a pressure of 1 atmosphere, or solutions with a 1 molar concentration. And for a chemical process, where the reactants and products are present in the standard state, we take the Gibbs free energy change. So that's equal to the change in enthalpy minus the temperature by the change in entropy. And this measures whether a process proceeds without the input of external energy. So generally, nature moves towards low energy and high disorder states. So therefore, for an exothermic reaction, the change in enthalpy is less than 0, and where the products are more disordered than the reactants, the change in entropy will be greater than 0. And we will explore this further when we look at thermodynamic favorability. We can use the standard Gibbs free energy change to determine if a chemical or physical process is thermodynamically favorable, or in other words, the process occurs without the input of external energy at a given temperature. And the condition for thermodynamic favorability is that the Gibbs free energy change is less than 0. Now historically, the word spontaneous was used, and that means the same thing as thermodynamically favored. So for example, if we have a phase change from water to ice, well, we know that heat was lost, so therefore the change in standard enthalpy is less than 0 for an exothermic process, and when water turns to ice, it becomes more ordered, so the change in entropy is less than 0. And therefore this term is negative, and this term here is positive, because the entropy was less than 0. And therefore we say that this process is thermodynamically favored at low temperatures. And this is true because water freezes at 0 degrees Celsius or 273 Kelvin. The standard Gibbs free energy change for a physical or chemical process, and typically we look at chemical reactions, is equal to the sum of the free energy of formation of the products under standard conditions minus the free energy of formation of the reactants under standard conditions. And the Gibbs free energy of formation is really the energy change due to the formation of 1 mole of a substance from its constituent elements under standard conditions. And this is typically at a temperature of 25 degrees. So given a chemical reaction, we simply subtract the free energy of formation of the reactants from the free energy of formation of the products. And these are already given in tables. The free energy of formation of molecules like hydrogen gas is 0 because they already exist in their standard state. And it doesn't take energy to form hydrogen gas from its constituent elements. Generally, we can calculate the free energy change of a process given the standard change in enthalpy and change in entropy. So for an exothermic process, which has a positive change in entropy, then this term is negative, and this term here is positive. So subtracting these two, the free energy change is always going to be less than 0. And therefore the process is thermodynamically favored for all temperatures. And if the process is exothermic and the change in entropy is negative, then this term becomes negative. So therefore for the free energy change to be less than 0, the temperature must be low. So the process is thermodynamically favored for low temperatures. And I'll leave it for you to verify that for the following endothermic cases, this process is not thermodynamically favored for any temperature, and this one is thermodynamically favored for high temperatures only. So effectively for these two cases, we don't really need to do a calculation to determine thermodynamic favorability. Is the following reaction thermodynamically favored under standard conditions? Well, we're given the standard Gibbs free energy of formation of the product, being ammonia. So the free energy change of the reaction is equal to the sum of the free energies of formation of the products. That would be 2 moles multiplied by minus 16.5 kilojoules per mole. And then minus those of the reactants. So we have 1 mole of nitrogen gas by the free energy of formation of nitrogen gas, and plus 3 moles of hydrogen by the standard free energy of formation of hydrogen gas. The free energies of formation of the reactants are 0, so we obtain minus 33 kilojoules because the moles cancel, and we can also write this per mole of reaction because you have 2 moles of ammonia per mole of reaction. So given that the standard Gibbs free energy change of the reaction is less than 0, then the reaction is thermodynamically favored. Under which temperatures is the following exothermic reaction thermodynamically favored? Well, given that the reaction is exothermic, the standard enthalpy of the reaction is less than 0. And given that we have 4 moles of gas on the left hand side and 2 moles on the right, then the standard change in entropy of the reaction is less than 0. So using the expression for the standard Gibbs free energy change of the reaction, we have the enthalpy of the reaction minus the temperature by the standard change in entropy. And given that these values are both negative, then what we get is negative minus a negative, which will give us a negative value plus a positive value. And therefore, for the free energy change to remain less than 0, then this temperature must be low. So the reaction is thermodynamically favoured under low temperatures. Processes can be thermodynamically favoured, such as the formation of elephant toothpaste, according to this reaction, or if you use the standard free energies of formation in this table, you'll obtain a value for the reaction that's less than 0. But we know this process, when it's not catalyzed, it occurs at an extremely slow rate. So therefore we say that the process is under kinetic control, or effectively being controlled by the rate of the reaction. And a high activation energy is a common reason for the process being under kinetic control. So if the process doesn't proceed at a noticeable rate, it doesn't mean that the chemical system is at equilibrium. So where the process is thermodynamically favoured and doesn't occur at a measurable rate, we can conclude that it's under kinetic control. Consider the homogeneous reaction involving gaseous reactants and products. Then we can write the Gibbs free energy of a reactant or product as the Gibbs free energy at a given temperature plus the universal gas constant by the temperature in Kelvin by the natural log of the pressure of the gas. So for a reactant I and for a product I, so therefore the free energy change of the reaction is equal to the free energy change at a given temperature plus RT by the natural log of the reaction quotient. And I'll leave the derivation as an exercise. Now at equilibrium, the Gibbs free energy change is 0, and therefore we obtain the following expression: if the equilibrium constant is greater than 1, then this term is positive, and therefore the reaction favours the products. And in a similar way you can obtain the following conditions. And you can apply some algebra to solve for the equilibrium constant, where you can draw similar conclusions on the effects of delta G naught on the equilibrium constant. Calculate the equilibrium constant for the following reaction at 25 degrees. So remember the relationship between the standard Gibbs free energy change and the equilibrium constant. And then if you divide through by minus RT and take e to the power of both sides, and now if we make our substitutions for the Gibbs free energy change, which will convert to joules per mole of reaction, and we divide this by R and we multiply it by the temperature in Kelvin. So the Kelvins cancel, and we can convert this as 1 mole of reaction per mole of nitrogen gas. So this mole of gas, which we can write as moles of nitrogen, cancels with this one. And then these units cancel, and joules cancel. So calculating this out, we obtain the following equilibrium constant. So the reaction strongly favours the products at 25 degrees, but we need to make a compromise, because if the temperature is too low, the reaction will be too slow and under kinetic control. At what temperature does the following reaction change from being thermodynamically favoured at equilibrium? We'll recall that the Gibbs free energy change of the reaction, which we can denote using this subscript, is equal to the enthalpy change of the reaction minus the temperature in Kelvin by the standard entropy change of the reaction. And here we assume the standard enthalpy and entropy changes are independent of temperature. So the reaction changes from being thermodynamically favoured, which is towards the products, to thermodynamically unfavoured is when the standard Gibbs free energy change of the reaction is equal to 0. So we substitute the standard enthalpy change, and we have the unknown temperature in Kelvin multiplied by the standard entropy change, which we convert to kilojoules per Kelvin mole of reaction. And now if we solve this equation for T, you're going to get cancellations between the kilojoules and moles of reaction. So if we calculate this out, we get a temperature of 464 Kelvin using 3 significant figures. One way to drive a thermodynamically unfavourable reaction is through the input of external energy. So for example, the photosynthesis reaction, where plants convert carbon dioxide into glucose and oxygen is released as a byproduct, requires the input of solar energy. Now another way to drive a thermodynamically unfavoured reaction, which has a positive free energy change, is by coupling the reaction with a thermodynamically favoured reaction. So for example, we have glucose reacting with an inorganic phosphate to create phosphorylated glucose, and you couple this with the hydrolysis of ATP, which is used to drive biological processes. And then because these two reactions share a common intermediate, well, the thermodynamically favourable reaction effectively consumes H2O, which drives this reaction to produce phosphorylated glucose. And a net reaction is obtained by summing up the two reactions and summing up the free energy changes. So therefore the net reaction is thermodynamically favoured. Galvanic cells use energy released during a thermodynamically favoured reaction to generate electricity. So if we sum these redox half reactions, we get a thermodynamically favoured redox reaction. So at the anode, oxidation occurs, where zinc is oxidized, and oxidation means a loss of electrons. And at the cathode, copper is reduced, and reduction means a gain of electrons. And this results in a flow of electrons from a higher potential. Now at the anode, we have an electrode in a zinc nitrate solution, and at the cathode we have a copper electrode in a copper 2 sulfate solution. So when zinc is oxidized, you have solid zinc converting to zinc ions in the solution, and when copper is reduced, you have copper ions attaching to the copper electrode. And here we have a voltmeter to measure the voltage. Now when you have excess zinc in the solution, negatively charged ions are attracted and flow from the salt bridge, and at the cathode you have a reduction of copper ions, so you get positively charged ions flowing in that solution. So the salt bridge completes a circuit. An electrolytic cell uses electrical energy from an external source, such as a battery, to drive a thermodynamically unfavored reaction. So for example, if molten sodium chloride is placed in a container and we insert inert electrodes, such as platinum, which do not react, and we attach those to the positive and negative terminals of a battery, then the electrolytic reaction occurs, and you have oxidation at the anode, which means a loss of electrons, and here negative chloride ions become attracted to the anode and become oxidized to form chlorine atoms, which combine together to form chlorine gas, and you'll see that in the form of bubbles. And sodium cations get reduced at the cathode. So you get reduction at the cathode, and reduction means a gain of electrons. So here you have the sodium ions, which are attracted to the negatively charged cathode, and turn into sodium and play it onto the cathode. Consider the following galvanic cell, and in part A, we'll determine which species is oxidized or reduced at the anode. So at the anode, oxidation occurs, and then let's write the redox half reactions. So assigning the oxidation numbers, zinc goes to Zn2+, and oxidation is a loss of electrons, so we add those to the right here. And the copper cation gets reduced to copper. So given that oxidation occurs at the anode, zinc is being oxidized. Indicate the directional flow of ions from the salt bridge. Well, given that zinc is being oxidized, you're going to have more zinc cations in the solution, and therefore the chlorine ions from the salt bridge flow in this direction to balance a charge. And copper is being reduced to copper solid, so therefore more positive ions flow from the salt bridge in this direction to balance a charge. And which electrode gains or loses mass? Well, zinc is being oxidized, so the electrode loses mass, and copper is being reduced to a solid at the cathode, so this electrode gains mass. The standard reduction potentials for reduction half reactions are typically given in tables, so given that this one is an oxidation half reaction, we'll just reverse this reaction and flip the sign. And these are standard potentials, where we have a 1 molar concentration of the species involved. Now the larger the potential, the more likely the oxidation or reduction half reaction is likely to occur. So for example, zinc is more likely to be oxidized than chlorine. And we can calculate the standard potential of the cell using the standard potential of the oxidation half reaction and the standard potential of the reduction half reaction. And note that for this reduction half reaction, for example, we multiplied it by 2 to match the electrons and sum up those half reactions to get the redox reaction, but we never multiply the potential by a coefficient because it's an intensive property that doesn't depend on how much of the species we have. We can determine the standard Gibbs free energy change for an electrochemical cell using the number of moles of electrons that result from the half reactions multiplied by Faraday's constant and multiplied by the standard cell potential, which is obtained by summing up the standard potentials of the oxidation half reaction and the reduction half reaction. So for example, for this galvanic cell, E0 is 1.10 volts, which is the same as joules per coulomb, and we have 2 moles of electrons per mole of reaction, and Faraday's constant is 9.6385 by 10 to the 4 coulombs per mole. So when the units cancel, the result here will be in joules. And note that the redox reaction of the galvanic cell is thermodynamically favoured, so we have a positive cell potential, and for thermodynamically favoured reactions, delta G naught is less than 0. So that's why we have this negative sign here. And by the same logic, this electrolytic cell has a redox reaction that is not thermodynamically favoured. Consider a galvanic cell that's driven by the following redox reaction, and assume the reaction occurs under standard conditions. Find the standard cell potential. So that's equal to the standard potential of the oxidation half reaction plus that of the reduction half reaction. So assigning the oxidation numbers, we can write the half reactions as follows. So given that these are reduction potentials, we reverse the reaction and thereby reverse the sign of the potential. And for the reduction half reaction, we'd multiply it by 2, so the electrons cancel, but we don't multiply the potential by 2 because it's an intensive property. So therefore, if we sum these together, and the standard Gibbs free energy change is calculated as follows, where we just calculated the standard potential of the cell. And if we substitute Faraday's constant, and this reaction results in 2 moles of electrons per mole of reaction. And to get this in kilojoules, we multiply by 10 to the minus 3, which gives the following result, using 2 significant figures. The cell potential under non-standard conditions can be determined using the Nernst equation. And recall that the Gibbs free energy change under non-standard conditions is given as follows, and noting the relationships between the Gibbs free energy change and the potential of the cell, you can substitute those in this equation and you'll obtain the Nernst equation. So Q is the reaction quotient, and for a standard cell where we have the same concentration of zinc ions to the reduced species, then Q is equal to 1. And note that for a concentration cell, then Q in this case would be greater than 1, and the cell potential under non-standard conditions would be less than E naught. So if the reaction is thermodynamically favoured, where E is positive, then the reaction will shift to create more products, and therefore the concentration of zinc will increase and copper would decrease. And electrons will continue to flow through the wire until this term becomes equal to E naught. And that's how we look at the Nernst equation qualitatively. An application of electrolysis is electroplating. So for example, you may want to deposit silver onto a copper coin, and to do that, use a battery which results in silver losing an electron or being oxidized at the anode, and at the cathode, the silver ions are reduced, which results in a silver solid being deposited on this copper coin. And using Faraday's law, which states that the current is equal to the charge per unit time, which is in coulombs per second, which is the same thing as amperes, and we want to use this to determine the mass of silver that was plated onto or deposited onto that coin over some time t. So for example, you may be given a current and the time in seconds, then you'll be able to calculate the charge in coulombs. And then using Faraday's constant, and from this we have 1 mole of electron per mole of silver that's plated onto that coin. And then using the molar mass of silver from the periodic table, you'll obtain your final answer. 127.1 grams of copper is plated onto another metal in a solution of copper 2 nitrate. Calculate the charge transferred in coulombs, and we're given Faraday's constant. So therefore copper has a charge of plus 2, and nitrate minus 1 in an aqueous solution. So we have copper being reduced by 2 transferred electrons to form copper solid. So we're asked for a charge in coulombs, so we'll start with Faraday's constant, which is in coulombs per mole of electrons transferred, and here we have 2 moles of electrons transferred per mole of copper solid that's formed. And copper has a molar mass of 63.55 grams per mole. And then we multiply this by the mass of copper that was plated. So if you check your units for cancellations, our final answer will end up being in coulombs. And the least significant figures is 4, so our final answer will be written as follows. Determine the mass of iron that's plated out when a current of 2 amps is passed through a solution of iron 3 chloride over 10 minutes, and we're given Faraday's constant. So here chlorine has a minus 1 charge and iron has a 3 plus charge, so when iron is reduced, 3 moles of electrons are transferred. Now using Faraday's law, the current is the charge transferred on time, which is in coulombs per second, or amps. So we have the time given in minutes, and we convert this to seconds, and then multiply this by the current, which is in amps or coulombs per second, so we can see the units that are cancelling. And then this is connected by Faraday's constant, which is in coulombs per mole of electrons transferred. And here we're cancelling out the coulombs, so effectively the same thing as dividing by this value. And we have 3 moles of electrons transferred per mole of iron that was plated out, and using the molar mass of iron, and that gives us the mass of iron that was plated out, using 2 significant figures.